Okay, so here we are going to understand the Lineweaver-Burk plot for non-competitive inhibition. Now remember, the Lineweaver-Burk plot is a double reciprocal plot based off of the Michaelis-Menten graph. So the reason why we prepare a Lineweaver-Burk plot is because we want to linearize the data that we have in our Michaelis-Menten plot so we can clearly identify our Vmax and our Km value. Now in a Michaelis-Menten plot, Vmax is an asymptote. So an asymptote designates a value that we are going to approach, but we are never going to reach. So since we cannot clearly determine what Vmax is in a Michaelis-Menten plot, we cannot determine Km either, because Km is 1/2 of our Vmax. So what we do instead is we linearize the data. How do we linearize the data? We take the reciprocal of our velocity values, and we take the reciprocal of our substrate concentrations, and when we plot them, we get a linearized data which follows the equation of y equals mx plus b, where y is our y values, m is the slope, x is the x values, and then b is the y-intercept. Now for a normal enzymatic reaction with no inhibitor present, we can see the following line. But when we have non-competitive inhibition inhibitors present, we can see there is a change in our plot. Now we have to understand two things from this graph. We have to understand where is our Km and where is our Vmax. So Vmax is going to be our y-intercept. So we can note that our y-intercept is designated in this equation as b, but we can replace the values in this equation with values that correlate to the Lineweaver-Burk plot. We know y values are going to be 1 over our initial rates. 1 over initial rates. Our x values are going to be 1 over substrate concentration. So we have that. And then our slope is going to be Km over Vmax. And then we have our y-intercept as 1 over Vmax. So our y-intercept, these are our two y-intercept values. These are 1 over Vmax. So if this is 1 over Vmax, if we take the reciprocal of this value, we can determine the Vmax. So we can note from the Lineweaver-Burk plot that our 1 over Vmax value has increased in presence of a non-competitive inhibitor. But the 1 over Vmax value, since it has increased, if I take a reciprocal of a larger value, I will get a smaller number. So if this has increased, the 1 over Vmax value has increased. If I take the reciprocal of a larger value, I will get a smaller value in return. And if I take the reciprocal of a smaller value, I will get a higher value. So it appears that our Vmax has increased, but that would be incorrect. 1 over Vmax has increased, but if we take the reciprocal to actually determine what Vmax is, we can understand that Vmax has actually decreased for non-competitive inhibition. And we can actually see that in the Michaelis-Menten plot, where we can see our Vmax has decreased. Now, the y-intercept represents our Vmax, 1 over Vmax, but our x-intercept is what represents our Km value. Remember, Km is the substrate concentration at 1/2 of your Vmax value. So we can note over here that the x-intercept is actually going to be the same for non-competitive and normal enzymatic reactions. And we discussed this previously in the Michaelis-Menten video, but why does Km remain the same? Well, when a non-competitive inhibitor binds to the allosteric site of the enzyme, it just renders that enzyme inactive. But in a solution, you have many different enzymes. You will have some that are inactive and you will have some that are active. The ones that are active will have the same Km value as a normal enzymatic reaction. Because remember, Km refers to affinity. A high Km value means low affinity, and a low Km value means high affinity. If there is no inhibitor bound to an enzyme, its Km value, its affinity for substrate, is not going to change. So that's really important to understand. So when a non-competitive inhibitor is bound to an enzyme, it's going to make it inactive. but in a solution, we have both active and inactive enzymes. And for the active enzymes, we will see that the Km value, the affinity for substrate, stays the same. Now, you may be wondering, why does Vmax decrease when we have non-competitive inhibition? Well, we discussed that previously, but we'll go over it here again. Our Vmax has decreased because, remember, a non-competitive inhibitor binds to the enzyme and makes it inactive. So in a solution, we have reduced the number of available enzyme. If we reduce the number of available enzyme, we have a lower concentration of active sites present for substrate to be converted into product. So we have to understand the key relationship, which is enzyme concentration is directly proportional to the rate of the reaction. The more enzyme that you have, the more greater your rate of reaction will be. And since in non-competitive inhibition, we are lowering the concentration of enzymes, we will see a decrease in our Vmax. And that is essentially the Lineweaver-Burk plot. This is the most important equation we have to remember, because with this equation, we can determine what is our Vmax, and we can also determine our x-intercept, which will give us our Km value. And the whole purpose of this Lineweaver-Burk plot is to clearly understand what our Vmax and Km are. It's a linearization of our data that we obtain through the Michaelis-Menten plot.